what is dynamic load balancing? The goal is essentially to repartition an existing distribution such that you have equal work and low communication costs and a low cost of reshuffling the data. And this typically occurs after some kind of change in the work assigned to each processor, such as mesh adaptation. So I wouldn't be up here if FASTMath didn't have a bunch of tools to do these sorts of things. So looking at an adaptive workflow, we start with some kind of application initialization up here. We then do an initial partitioning of the data. We run our application, let's say a solver of sorts. We then adapt based on that solve. And then we, now that we've changed the work on each processor, we need to redistribute. And we run a dynamic partitioning to do such things. And again, the goals are restated here. And this loop continues until your application has concluded, whatever criteria is conclusion. So what's required of a dynamic load balancing tool? It must run side by side with the application. As you saw in that loop, you're already distributed. So whatever concurrency level your application's at, your dynamic load balancer has to be in that realm. Otherwise, you're going to be a bottleneck in the overall workflow. Now, there's tricks to not have it run at the same exact concurrency, but for the most part, you can consider it the same. So because you're at this level of parallelism, some of our best solvers are at hundreds of thousands or millions of parts or 750,000 cores. You have to be fast, scalable, and not be a bottleneck again. To interface to these applications, you have to have an easy-to-use API for your tool. So, C interfaces, Fortran interfaces, C++, some mechanism to get your data in and get the partition assignment out or tell the tool how to repartition your data. So if you contrast this against what we call static partitioning, where I'm starting with a single collection of all my domain data and I'm sending it out to a set of processors, the challenges are much greater on the dynamic side. And performance is much more critical. On this, when I'm doing one-to-n partitioning, it can run for a long time, and I'm not burning up a bunch of CPU resources in my precious allocation on some large system. So the Zoltan and Zoltan 2 toolkits provide a large number of partitioning tools you can use for both static and dynamic. We're going to focus on the dynamic tools. So these can be roughly grouped into two sets. The first is the geometric partitioners. So this is when you have objects and you can somehow define spatial relations between them. So and the general approach to do the partitioning is to recursively section the data. So the bisection techniques or the most common bisection techniques are the recursive coordinate and recursive inertial. Where the inertial tends to track the geometry of your domain better. If you have kind of an L-shaped or something, it's not just going to fire cut lines on the axes. And then you have a multi-section technique, multi-jagged, and that's in Zoltan 2. The second group of approach or techniques are the topology-based tools. So here your objects have data dependencies defined between them. So you can think of, there's some kind of communication that has to occur, some kind of exchange of information there. So, if in this bottom image, if these nodes are your data objects and then edge represents a dependency, now we can make a partitioning decision that tries to minimize the number of dependencies that we're fracturing or splitting across a partition boundary or a process boundary. So the two groups of partitioners within the topology category are the graph and the hypergraph. And I have a slide that will illustrate this a little better. But the most powerful tools, or the most common tools, are Primetis and PT Scotch for graph partitioning, and then PATOA and the Zoltan PHG for hypergraph. So in geometric partitioners, the general approach is, well, I want to make sure I have equal workload on each process, and that's standard for any partitioning tool. And I'm going to do this by sort of clustering data objects that are spatially close together. So the advantage of this approach is that it's conceptually simple It's also fairly simple to implement. You can do this in a few hundred lines or so for a recursive inertial bisection. It's fast to run, and it's fairly inexpensive. When you don't have connectivity info available, this is a good option. And there's some applications that can benefit from this kind of approach. The key disadvantage here is that you're not modeling communication costs. So while your parts will be well balanced, their shape will sometimes be poorer than the graph approaches. And if you look at these partitions here, they're blocky. So they have typically a larger number of neighbors than the graph partitioners. And if we sort of zoomed in on one of these boundaries, you'd see it's fairly rough, and that induces more local communications. So the topology-based partitioners, again, they're trying to balance the work, but now we can try to minimize or reduce the communications between processes. And if you think of a graph and you know about min-cut, that's basically what we're trying to do. We're trying to reduce the number of dependency edges that are being cut. So if we're coming from an unstructured mesh application, here we have a 2D mesh that we're going to build a graph from and a hypergraph, and then pass this off to our graph-based or hypergraph-based partitioner. So the faces in the mesh become graph nodes, and shared edges between faces become graph edges. And then in the hypergraph, the concept is similar, except the hyper edges extend over multiple elements. And in general, this is people like this because it gives you a better representation of the communication, the real communications in the application. So the key advantage here is that you get higher quality partitions. You get all the benefit of the equal workload, and you get better shape, part shape, lower neighbors, smoother boundaries. The key disadvantage is that these are more expensive than the geometric methods, both in time to run and memory usage. And this is especially true for the hypergraph-based methods. And also, when you get out to large scales, the quality of the partitions and the runtime can start to degrade a bit. And when I say large, I mean beyond like 32K cores kind of thing. So a third technique says, well, we have this unstructured mesh. Can we leverage the adjacency information that the mesh data structure is storing to make these partitioning decisions quickly and move data as minimally as possible? So in the unstructured mesh representation, for mesh adaptation, we typically require a complete representation. So, and this gives us constant time access to the adjacencies. So there's our quick data access. Now we just have to make quick decisions. So a very easy way, or a good way to start to use these, is with a diffusive procedure. So here I'm just going to make subtle changes at the boundaries that are locally optimal and try to reach a global optimal criteria. So in addition to the mesh adjacency structure, we also have the partition model. So this basically tells me at a coarser grain what things are communicating, and that can be helpful as well. And with all of this adjacency and partition model information, we can account for multiple entity types fairly easily. And with this multiple entity type approach, we're able to run these algorithms that improve the scalability of some solvers after we run a standard partitioning tool like RIB or ParMA. And we've done this with really big meshes. So to quickly hit the high points on the algorithm for this multi-criteria improvement, the application gives us a priority list of entities that they want balanced. We traverse the priority list, and each entity type, we balance that type. Now, the key is when we're balancing, the balance of a high priority entity is not sacrificed when we're balancing a lower priority entity. So this preserves that hierarchy that the application is requesting. So an example of this is you have a finite element code whose assembly is sensitive to the balance of the mesh elements, but the solve procedure is sensitive to the balance of the vertices where the DOFs are being held. So we want to first balance the vertices and then balance the elements. So in this case, this diffusive ParMA is able to reduce the vertex imbalance or the DOF imbalance by nearly 10 percentage points, and only increase the element imbalance by roughly 2 percentage points. So, like I said, we're willing to sacrifice the lower priority entities for the higher priority entities. It goes both ways like that. And with this approach, you typically see a positive effect on your strong scaling of the application. And it's not uncommon to see a 10% improvement at very large scales and small part sizes where your graph partition tends to become an issue. So going back to the adaptive workflow, we've been talking about doing dynamic load balancing after adaptation. But what if we did it before adaptation? And why would we want to do this? So if I'm adapting my mesh and one part's going to be refined a lot, right? The processor that is assigned to that part may not have enough memory to hold all that mesh. So we need to predictively balance to first avoid running out of memory. And then second, if we do it right, we can possibly have a load balance after adaptation that gets us close to what the solver wants, or closer. So the basic idea is to take the information that drives mesh adaptation, use that to compute weights that we assign to the mesh elements, feed those to the load balancer, whether it be a graph, geometric, or a diffusive ParMA-like procedure, and then perform the load balancing, and then perform the mesh modification. So again, if this all goes well, we get this nice even distribution, where before we had this hills and valleys things with spikes that may have killed us. So looking at all these tools that we have, the FASTMath partitioning tools are able to ensure the ability of applications to achieve and maintain scalability. A couple examples of this are we have the Zoltan multi-jagged partitioner with the multi-grid solver MOAB. Apologize if I'm butchering the name. To have a scalable partitioning tool to over 500,000 cores. And with ParMA, via Zoltan, we're able to do a similar thing with PHASTA CFD, where we have a 92 billion element mesh on 3.1 million parts and 700,000 cores. This is a Mira run. So towards these tools, or extending these tools, are architecture-aware pieces from the Zoltan folks. So the first is a hierarchical partitioning tool, where you first partition to the network, and then you partition to the nodes, and then the cores. And this can be defined in as many levels as you need, where you somewhat get this tree of partitioning results. So a simple example on a matrix vector multiplication on 96 parts of Hopper, you can see nice improvements in the overall runtime, or the normalized runtime, for some different matrix partitioning examples. And then they have a task placement approach, where the idea is to assign MPI tasks to processing cores such that the communication between the application tasks is reduced in cost. So imagine if your process over here and your process over here have to communicate, and they're on different ends of the network, that may be more expensive than if they're on the same node. Right? So it tries to get that mapping closer to an ideal one. And it does it by running successive applications of the multi-jagged partitioner, and preserve an ordering between these applications such that you get the mapping. And on 64,000 cores of a Cray system, Cielo, with the mini Ghost application, mini app, a 34% decrease in the average execution time is yielded with this mapping over a default distribution of the data. So at that, I'll hand it off to Vijay, who will bring us into the integration of unstructured mesh codes and the solver.
This part of the talk is more about how we actually interact with the solvers themselves. So once you have created unstructured mesh, we dump it into a file with the partitioning information. We got to load it back up into an application, and what sort of interfaces and what sort of interfaces are available. So I'm going to briefly look at two specific application areas. So One is related to the Sigma tool that we talked about more about MOAB and its interface to PETSI. The other would be FASTA and its use of the unstructured meshes and also its integration with PETSI. So the basic key ideas are that we need good meshing infrastructures, and we need partitioning tools, and we also need pretty scalable interfaces to the solvers. If not, you're not going to solve real-world problems pretty quickly. So we also need interfaces to actually define the fields and to form the discrete system of equations in memory. So both of these interfaces actually show sort of briefly, and will actually show how these kind of interfaces are put in practice. So I'm going to talk about the MOAB-based DM implementation, and Mark will take over and talk more about the FASTA implementation. So the MOAB Discretization Manager is a specific implementation of the DM interface. So we actually created a specific implementation for DM that sits on a native MOAB mesh so that you could use array-based data structures provided by MOAB. So you could basically load up the unstructured meshes with the partitioning information in several different formats and use that to discretize your partial differential equations. And while doing efficient unstructured mesh traversal and defining your fields and creating your linear operators in memory, and then pass it on to the scalable PETSI solvers that are already available, both the linear, nonlinear, and the time-dependent solvers. So the DM pretty closely integrates well with all of those solvers. So the basic idea is that the DM MOAB interface, or more DM, actually wants to provide the ability to make it easier to discretize your partial differential equation using different types of maybe finite element method and finite difference methods. So the actual design for DM MOAB also closely represents the structured DMDA and the unstructured DMplex interfaces that's in place already in PETSI. So what that means for a user is that it's easy to get started with the new interfaces. So it improves software productivity. The MOAB interface also supports both the strided and interleaved access. So that opens up a lot of ideas for better preconditioning strategies, especially when you're doing multi-component problems. Right? You could do block preconditioning, or you could choose to create couple operators or not, and depending on your problem of interest. It also kind of abstracts out the layer of the unstructured mesh traversal, because we use the MOAB-based iterators underneath, which are contiguous in memory, so the traversal is pretty quick. And we're also trying to optimize what are called tags in MOAB. So those are essentially either integer or double precision data that are defined on entities in a MOAB mesh. We can use those contiguous in memory data and define a PETSI vector right on top of that, and it seamlessly gets into the whole framework of the solvers, and the user doesn't necessarily have to do anything to actually access the memory management or do any sort of memory management. There are also interfaces and API functions to define different field components, to manage the degrees of freedom, to actually query the degrees of freedom and assemble your linear system. The vector local to global transformations are also provided. So this DM MOAB interface is actually part of the latest PETSI release. So you can actually look it up, maybe try out a few examples there. So the original motivation was a plasma surface interaction project, which actually has several components that need to be solved simultaneously, and they could be pretty strongly coupled. So we wanted the ability to actually minimize the memory storage, and that's one of the motivations behind reusing the tag data in PETSI vectors. And by providing the interface to DM, we also get the ability to use different IMEX solvers provided by PETSI, so that we can treat few of the stiff components implicitly and the others explicitly. we also added some capability to reduce the memory storage in the linear operator by having, or at least providing the capability to specify what part of the couple linear operator that you want to form in memory. So you could optionally create some of the couple terms and not allocate for some others. And so you could actually play a lot of different games, even in terms of the preconditioning there. So there are two relevant examples. One is the 1D later example in the time-dependent solver, and the second one is the 2D sort of Laplacian solver.
Okay, probably about 10 times we've told you about 92 billion elements on 3/4 million cores. The particular code that does that is, the author of it actually calls it PHASTA. That the original author is Ken Jansen, who's at the University of Colorado. It is a highly scalable CFD code. It uses stabilized finite element methods and uses a very particular method of solving that takes direct advantage of the partitioned mesh. And that, to do that well, requires use of basically diagonally dominant preconditioning techniques, which the stabilized finite elements support effectively, basically because they produce well-conditioned systems, even in highly anisotropic meshes. Elements with 10,000 to 1 aspect ratios are not uncommon at all in problems that we're doing. So this is a code that has been under development for a number of years and has shown excellent scaling out to the full Mira system. Now, as we look at extending that code to possibly doing other types of problems where the physics will be even more ill-conditioned, we would like to be able to make effective use of PETSI solvers. So part of the activities, similar to what Vijay was talking about within FASTMath, is looking at how we would do that with this code, and can we get the same degrees of scaling with that. And where we stand on that is that we have integrated it fully with PETSI and have very interesting results. Now, if you run, and the bottom line of the results is if you run to a very high tolerance, very high accuracy on your nonlinear solves, you want a lot of significant digits, then PETSI tends to be faster. If you slightly lower, which Ken often uses for most of his simulations, the 4 or 5 significant figures as opposed to 8 or 9 or 10, then the current native solver is faster, but they've identified exactly where the bottlenecks are, and it's in the expected area of that. And one of the reasons we get the good scaling is we don't really do a standard assembly type of process at all. It's really on a part-by-part basis. So it's a bit different than the standard methodology. So it's in the assembly process, but in interacting with Jed Brown, they believe that they're going to be able to address that very effectively, so there's continued work there. So that's another aspect of having the solver people working fairly closely with the people that do the discretization / meshing technologies. I'm going to jump to a slightly different aspect now, and that is using these tools to create adaptive loops, and I hope to address the question that had come up in doing that. The driver here from our perspective is applications that are out there. They have existing high-performance analysis codes that can solve the problems, but they don't have the meshing technology. They don't have the mesh control technologies for adapting the meshes. They don't necessarily, and they can't deal with the load balancing issues effectively unless it's a fixed mesh. How do we bring all those pieces together? And the key of that is how do we use these mesh infrastructures, be it Sigma or be it ParMA, to be able to control that. So within that, if you look at this infrastructure, something that if we had more time we would have explained much more carefully, but we're really relying on a generalized abstraction of domains in terms of topology and the adjacencies of topology, both at the geometric model level and at the mesh level for this. These parallel infrastructures are really taking advantage of that. That helps maintain the linkage back to the geometry and the linkage forward to the field information, partition control methodologies, and dynamic load balances techniques, as you saw in what Cameron did. So now, how do we go about attacking the needs of applications? And there's a couple of approaches. What I'm going to talk about here is to try to use things at a bit higher level in terms of how we interact with the analysis codes. And the driver for that was applications come to us and say, well, we don't really want to write a lot of this. We want you to provide us tools so we can plug in a little bit more easily or with minimal changes. We're not writing a new code from scratch. We don't want to try to take full advantage of all your APIs. We want to just do it without you killing us on doing a lot of new things. Now, if you're writing a brand new code from scratch, that's not the optimal approach. But if it's an existing code, it's a fairly strong approach. So the idea is, can we have this parallel infrastructure interacting with all the pieces where now the whole analysis code here is one little box. Now, when Glenn speaks, he'll talk about Albany, which will be one of the codes that we use here, and you'll see that that's really a much bigger thing. But this picture is centric on how do we control the interactions all the way from problem specification through all the adaptive processes in that. So now, a pragmatic driver of that is very often when applications came to us, they said, you shall not touch our application. And by the way, our input is via files. So we will set up and use this structure. We will use all our detailed APIs. We'll write all our interfaces to your file structure doing that. But then what we'll do is when you start finding out that file I/O is your bottleneck, we'll tell you, well, if you let us in to look at your I/O routines, and or you look at your I/O routines, we can take and, because we've done everything with APIs, instead of loading the file structure, we'll just load your data structures directly. So the price for this is you have some duplication of data structures for at least some period of time. You can recover that, some of it you may want to maintain so you don't have to rebuild it. And what is the advantage of the in-memory? I make it sound like it's very easy, and it's, the software for it is not so trivial. But what happens with that is now, instead of having something that gets worse as you increase the number of processors, that is a file-based interaction for this fairly simple problem at a fairly low core count. It took 49 seconds, and when the core count went up was 91 seconds. Within memory only takes 2 seconds and 1 second. So that's at least my first level answer to your question of how do we start working with applications that are existing applications. And we've actually done this with a wide variety of codes. Of course, it's somewhat expected. You're going to see some examples where we use PHASTA, because that's a code we've been working with for a long time. But I'm just going to point out some of these examples. So active flow control problems, where we're solving Navier-Stokes using level set methods. Well, it would be also in the next example for dealing with multi-phase flows. Error estimations with anisotropic mesh adaptivity, and we're doing problems such as this with adaptive boundary layers. You saw a couple of examples of that type previously. The same analysis code for dealing with two-phase flows, where now the level set, we're adapting not only based on the discretization error, but based on the level set to follow the injection of fluid through a gas. Aerodynamic simulations, in this case for NASA with the Fun3D code, we're using some of the same things, although now it's a different, more sophisticated error estimator based on goal-oriented techniques, but still anisotropic. Oh, and I should mention over here, we're bringing in things in these cases always from some high-level geometric representation. As before we can interact with them, they need to be a complete geometry representation, such as a solid model. And we typically use, in our case, ParaView, but Visit ParaView, do a nice job of the visualization of these things. So in this case, just Scramjet examples. Electromagnetic analysis, this is the ACE3P suite from Slack, in which case we've integrated with their higher order methods. So these have curved finite elements, and it's been coupled with a combination of finite element pick methods to track particles. So we've been able to do these higher order meshes and adapt to them quite nicely. with the same things. And all the examples I am showing today are done with in-memory, although two of them started off first with a file-based. Now Albany, for structural analysis applications, is actually being done for IBM. We're using the Albany Trilinos suite, and Glenn's going to talk in more detail about the Albany side of that and how we really put some of the pieces together at not quite as high level as I'm talking about here. But one part I do want to mention is the interesting thing is the geometry information that they actually use, their design information, is 2D layouts and process knowledge. So we actually have to, our biggest challenge on this is constructing these geometric models that have millions of parts in it. We actually have to do parallel geometry construction is a challenge we've got to figure out how to resolve, and we're using a tool called GeoSim for that, which is a commercial piece of software, but one that we can interact with fairly nicely. So in this case, they want to do full circuits. They don't want us to show real geometry, so we just got a thing with a bunch of deep trenches where it comes from these GDS2 files. We construct the solid models and then make the meshes of millions and billions of elements they want. So at this point, I'm going to let Glenn is going to take over and describe in a little bit more detail how we brought the things back together with Albany. The one comment I wanted to make is the interesting thing with Albany being a much more modern code, much more component-based to begin with. When the student had started to work on this, started looking at it, the first thing he wanted to do is everybody sort of knows, from at least from an engineering, people that come from an engineering world, how to deal with files. He wanted to do a file-based interface, and they were getting stuck on that. And I sort of strongly suggested, why don't we just look at in-memory? And the next week, the in-memory one was working, so it's nice to have a code that implementing the in-memory is very fast. And Glenn, take over. Thank you.
Thanks, Mark. So thanks for the introduction, Mark. I'm going to go through a few slides here that talk about the Albany code and how we're interacting with the parallel and structured mesh infrastructure that Scorec is developing. And Albany is a kind of a fairly standard finite element application. Finite element, unstructured mesh, implicit solvers is the strengths of the code. It uses a lot of Trilinos capabilities. In fact, one of the origin statements of Albany was to use as much of Trilinos as possible within a single application. So at some level, it's a demonstration prototype for the capabilities in Trilinos and how to combine those together to make a finite element code. It's also a mechanism to demonstrate this agile components-based software development strategy. So that's a strategy whereby can we create a collection of generic components and combine those together in extensible ways to create, a finite element engineering analysis application or other tools like that. So Albany is the instance of the first one. So it shows how you can do that. It shows how you can use template-based generic programming to make very generic interfaces. For example, residual functions that you can use to form the actual residual of the physics system. Then you can use a forward AD mechanism to form a Jacobian, basically a quote analytic, unquote Jacobian, based off of using that residual function. And then you can continue on and form all manners of other types of derivatives, tangent matrices, uncertainty quantification derivatives, etc. And all this can be done with basically the generic template interface to the residual function that defines the physics in the code. It's a Trilinos demonstration application. We use on the order of 98 different Sandia packages and libraries, depending on what type of Albany executable you want to design. You can design, you can put one together that's just basically mechanics, or you can go through and add a lot of additional capabilities, at which point you'll use more packages. So it's Albany is on GitHub. In fact, the link to it's on the exercise main page. You can go through and take a look at some of the more detailed capabilities there. The example set's there so you can get an idea for the diversity of physics that you can solve this way. It goes, we have some quantum quantum device design calculations in there, fluid dynamics, thermal mechanics, some basic fracture capabilities, et cetera. And there's a whole suite of example problems there that form the test suite for Albany that you can look at. A typical Albany user will go through and take an existing example that's close to what you'd like to build and edit that to move forward. So there's enough examples in there to kind of provide a base for people to get started looking at different things. So here's the Agile components methodology on a single slide here. Basically, most of these capabilities over here are out of Trilinos. Here are the Scorec mesh tools. We're using certainly the basic mesh database, parallel mesh adaptation capability. We evaluate and form size fields in here to drive the mesh adaptation process. We're using tools for load balancing, dynamic load balancing, as we adapt the calculation and move forward with it, et cetera. Then the rest of these capabilities over here are out of Trilinos, so we leverage the Trilinos nonlinear solvers, linear solvers, many core capabilities. COCOS is being used as part of the TPETRA finite element data structures to give us a multi-core parallel capability. These are PDE assemblies, field manager discretization tools out of the Piro package of Trilinos. And then the Staccato package is used for UQ capabilities and forward AD to form Jacobians, so on and so forth. Moving on here, how does this work in application? So one of our first applications that we've been working on in the last couple of years is ice sheet modeling. So Felix is the name of the project. Basically, it stands for Finite Element Land Ice Experiments. So we're looking at a problem over here where we have an ice sheet flow over the structure of the continent of Greenland here, and looking at how to model that, what type of physics we need to have, and how to do this in parallel, what type of preconditioning. So we're using multi-grid preconditioning for this. Getting pretty good scalability results. I'll look at that here in just a second. And the code base here is Albany. It's basically, we're able to link to multiple discretization environments, but one of the one we're focusing on here is basically the Scorec tools. So the combination of Albany and the Scorec tools is the PALS package, so Parallel Albany Adaptive Loop of Scorec is what that stands for. Moving on here, scalability, this is what it looks like basically. So this is a fairly new project. It's a little over a year old. And so we're getting pretty good scalability. We're not pushing the core count up real high yet, but here's weak scaling on the Greenland ice sheet calculation that we just looked at, and basically different resolutions of the model as we're going up here in number of core counts. So that's what we're looking at. Basically, this is the total time minus the mesh import time, so we're not counting I/O in this, and finite element assembly time, and total linear solve time, and they all look reasonably well. We're pretty happy with this as it stands now. Relative speed up, that's comparison against the 64K baseline. Moving on to other activities, another one of Albany's strengths is the solution of finite deformation plasticity problems, just general large deformation mechanics. We're looking at extending this in the regime of fracture and the like. So some of the prototype projects we're looking at is basically looking at weld failure, large deformation of welded joints. Porosity in the weld leads to several different failure scenarios that we're interested in seeing how those evolve. Adaptive capability is mandatory for this. In fact, the example problem that we have for Albany is motivates a weld failure application and talks about why porosity impacts the evolution of the weld failure problem. Looking at adaptivity here, so this is an example. Here's the initial mesh, and basically all-tet mesh and uniform element size. And then as we drive the deformation forward, you can see the nice coarsening in areas where we're not needing to capture, the curvature in the stress field. And then there's areas where we have a lot of things going on that the mesh is adapted pretty nicely in here. So need to do this in parallel, need to do it to where we keep basically the same amount of workload on each MPI process. So this requires load balancing as the calculation proceeds. Basically what we'll do is we'll go through every few load steps of the calculation, determine if adaptation is necessary, and then perform that step, and then load balance right at the adaptation step. Moving forward, there is a significant capability for embedded uncertainty quantification in Albany. and we want to add adjoint capabilities to that. So there's also a thrust moving forward for additional UQ and optimization tools inside of Albany. The last application I wanted to touch on here is picking up from what Mark said, is looking at the mechanical behavior of integrated circuits during the manufacturing process. So there's all kinds of physics that goes on, thermomechanics primarily, as you're doing a manufacturing of silicon wafers. So you'll go through and you'll manufacture these at elevated temperatures, and then when you cool them down, the temperature change will induce thermomechanical stresses in the components, and it can cause problems with residual stresses or material failure. And the modeling project here is to describe that behavior of the cool down as we're manufacturing thermomechanical integrated circuits. And the complexity in here, there's a lot of geometric complexity, and you need to have adaptive meshing to focus on important features, to focus on some of the edges and the joints to be able to resolve maybe the creation of an incipient fracture condition or something like that. Creep is important because creep will relax the stress over time, so you'd kind of like to have creep in some situations, so we need a creep model in Albany, and that's work is also underway. Questions?
Just curious, how easy or hard is to set up a problem in Albany?
Depends on the problem. So if you're doing something fairly straightforward, if you're doing something that can be described as a square domain, you can use an internal mesh generator that's a part of the code that'll do simple meshes like, a single block, kind of a rectilinear type of a mesh.
For something like you show a more complex part.
So most of the work is in the generation of the mesh, and running the code after that is reasonably straightforward. But the generation of the initial mesh, getting the geometry the way you want it, getting the features meshed in that are important in your calculation, a lot of the time that's iterative. So you'll do it, you'll run the code, you'll find that you're not getting the type of result, the type of output that you want to have, and then you have to go back, remesh, and then try it again. And there's time involved in that.
Just a follow-up comment on that. In the demonstration where we show the PALs, we're going to be using a commercial mesh generator that is fully automatic and highly reliable. If you give it a CAD model, a proper CAD model, it will create a mesh. And if you're using adaptive techniques, you now don't have to be so concerned about making that initial mesh so perfect. It will take care of that, the adaptive procedures. You just have to, literally, you can give it a CAD model and press a button, it will make a mesh. It will be a valid mesh.
Right. So following up on what you said, when you do the adaptive mesh refinement, so you are going to conform with the boundaries?
Absolutely.
So you would keep track?
All the adaptation goes back to the CAD model for any geometric information. And in fact, in some higher order applications, we're integrating with some higher order codes that I didn't talk about today. The higher order code interacts with the CAD modeler. The analysis code actually acts the CAD modeler for information when it's doing its numerical integrations.
Some CAD models, some CAD packages, actually, they don't export the geometry.
We don't rely on that for what we do. We interact directly with, it's a much longer answer, but we know how to deal with that. We have solutions for that, including doing that on a for example, we can support that on a blue gene on a parallel geometry.
Thanks.
So this is just an introduction to
Is there more presentation to the
the hands-on session. We have two sort of separate streams. One is with the Sigma tools. So it's basically two different workflows, so to say, because with the Sigma tools, you start off with the API descriptions. We go through different process of loading the mesh, creating the mesh, and then using a Laplacian solver, using that particular mesh that you generated. While with the PUMI symmetrics PALS workflow, you actually start off with a larger application, and then we'll break it down and describe the details involved. So I'll just quickly run through the introduction for the Sigma-based hands-on tutorials. So this is just a recap of what we looked at before yesterday, actually. So Sigma has 4 major components, at least that I'm going to cover here. So we start off with the continuous domain geometry, which is basically described in the CGM-based tools, and we generate a discrete domain when we mesh it with different algorithms. So most of those algorithms are part of MeshKit, and what you end up with is a mesh data structure, which is in a format that's understandable for MOAB, and so it reads it up in array-based data structures and lets you traverse the mesh. And with the DM MOAB interface that I introduced earlier, you could use the MOAB mesh and then do your finite element based solvers. So there'll be 4 major examples. One is a parallel example, which is basically hello MOAB in parallel, where we'll load up a mesh and look at some of the base APIs, how to create the data structures and the different options to load a mesh file in different formats. And then it'll also include some sort of a querying information in there for different type of entities and of different dimensions and tag values. And then there is this piece that it's not shown here. It's called sets and tags. So we'll look at collection of entities as sets and querying information based on that, and also tags that are defined either on the entities or a collection of these entities as sets, and how we actually define the parallel partitioning information in these sets, and how we can access them, how we can access the material data information, the boundary condition data. So we'll go through some of those in one of those examples. And then we'll come to the large mesh example, which is a it starts with a cube domain. You could specify the dimensions, and it'll generate a d-dimensional parallel mesh, both hex tets. So basically, tensor product elements and simplizers are supported in this particular example. You also have the option of defining tags, so we'll go through some of those details. And all of that is in parallel. So once you generate the mesh, we'll use that again in one of our DMOAB-based solvers. So once we dump out the partition file, we'll load it back up in DMOAB, create the data structures necessary to set up the discrete solvers. We'll define a field for the simple Laplacian operator, and it's actually a inhomogeneous Laplacian solver. So we'll go through some of the details, how the finite element assembly happens, and what we do to initiate the solvers, and we'll end up with the solution output and visualize that data eventually. So most of this information is in the Sigma site that are shown below. If you have any questions, you can email me or send an email to MOAB devlist. Thanks. So I'll hand it over to Cameron.
So as described, we're going to do a few hands-on exercises revolving around the PALS framework or interaction. So the first is a parallel mesh generation exercise where we're going to generate a 13 million element mesh on 128 cores of VESTA. It takes about 6 minutes, and this is obviously a non-trivial geometry. It's the one that Glenn showed you earlier. It's a upright from a formula hybrid car from RPI. So once we have this mesh generated, we then do in-memory conversion to the Squark mesh data structures, at which point we could do anything that our tools support. But for this example, we stop there at the mesh generation and conversion, and we just write out VTU files for visualization with ParaView. Following that, we do repartitioning of the mesh. We'll take a look at the initial partitioning that the mesh generation produces, see how it's sufficient for any kind of application you'd want, because it's a mesh generation partition, not a sort of classical solver partitioning. And we'll partition up to 512 parts on the same number of cores we generated on. We'll then follow that with the motivation for an in-memory parallel adaptive loop. As Glenn described earlier, it's a weld failure description. The example you'll run is the large deformation on the upright geometry. It runs on 1,000 cores. It's using parallel mesh adapt, quadratic mesh elements, SPR-based error estimation, local solution transfer of history-dependent state variables at quadrature points, And we use predictive load balancing to keep everything well balanced and efficient. And lastly, we'll do visualization of the resulting analysis results with ParaView. So,
Are there any questions?
We have time for maybe two or three questions.
Quick question. About the computer architecture that you are running these days, would you prefer architecture where nodes, some cores are stronger than others, like a heterogeneous node?
We've worked pretty hard with the tool chain that we're working on to be able to work on the machine, whatever the machines have. I mean, there was sort of the classic thing that you're stuck with a lot of your meshing operations, et cetera, on a serial machine. So we all had what we call hogs, which were big, 8 processor systems or whatever, but shared memory with tons and tons of memory on it. But those are very expensive systems. So we've gone out of our way to make sure the entire tool chain we're working with can run on a parallel machine. So for example, we actually have the ability to take CAD models and have those CAD models in a geometric modeling capability on the Blue Gene queue. So, and dealing with the memory distribution of that. Now, I'm not saying there's not times when on the queue, for example, for parallel mesh generation, if you've got it distributed over a large number of nodes, we may want to do the mesh generation just using one core and using more memory there just because that's going to scale better and might as well save the energy. But we don't have to. We've done parallel mesh generation on over 2,000 cores and that has fairly good scaling. And parallel mesh generation is a very hard thing to do in parallel. It is a hard thing to scale.
No, I'm thinking if there are serial sections in your code.
There are there's not only are there not serial parts of the code, there's not serial parts of the data at any point, right? The biggest bottleneck at the moment that we have to solve well is the initial CAD model. And we even have an ability to distribute the CAD model. Although at this point it's based on what a mesh tells it. We've got to do that before then, and an easy way to do that will be an octree. We already know one approach that we can take for doing that. Yes?
We learned during the past days that we should not, from the architecture guys, that we should not assume that the different processors have the same speed.
Right.
Have you already thought about how to take care of that with the load balancing?
Well, how we would take care of that with the load balancing is that there's the concept of assigning weights, right? And the weights can also go to the other end of saying, okay, I've got a stronger node. It either has more memory, faster capabilities, or whatever it can do. Have we actually done that? No. But conceptually, there's nothing particularly hard about that from a basic algorithm. The details of the software are going to get nasty.
Okay, one more question before we switch topics.
What is the plan in terms of multiphysics for Albany? Like, do you want to extend the range of physics that can be included, but also how is this going to be? For example, if you have a new set of PV, like new physics, would it be possible to have it coded?
Well, it depends on some of the details of the actual physics. So right now, there's a pretty wide variety of what I would say coincident mesh physics capability in Albany. So you have basically one form of your mesh representation, and you're solving your physics equations across that mesh representation everywhere. So for example, if you're doing like thermomechanics, you solve the heat equation plus the mechanics equations, and they're coupled with thermal strain terms and things like that, but they're on the same mesh. You can do that for a large variety of different type of physics applications. So it's fairly straightforward to add additional equations in, provide coupling. That's handled pretty nicely in the interface. In fact, that's what Albany was designed to solve, is coincident mesh multiphysics. Now, if you have
some domain varying physics, say thermal structural interaction or flow structural interaction. You might want to solve the Navier-Stokes problem over here and the mechanics problem over here and couple it at an interface, and you don't want to have mechanics DOFs out in the fluids or fluids DOF in the mechanics. That's much more involved, and Albany really isn't very well suited to solving problems like that you have a very, different sets of domains with, very different physics in the two areas. So that would take certainly more work, and typically what you want to do is you just live with having mechanics variables in the fluid side and vice versa, at least, to get a feeling for what was going on. But that, that's expensive. So Albany probably isn't the best tool to do something like that. So it really depends on what you're after and what you're going for. But if you can solve, if you're solving basically the same equations everywhere, then it works pretty well. So that's much more what it was designed to do.